Okay, so we're going to start electricity and magnetism. Well, we've been doing that for a while, but now we're starting electric circuits. So first of all, let's do some revision. All right, and this is stuff that you have done before, and we're revising it from grade 10 and 9. First of all, potential difference. Please, we do not call it voltage, it's potential difference. And it is the energy transfer per coulomb across a component. Potential difference refers to the difference in electrical potential energy. It is measured in volts. Okay, you know that, nothing unusual. You also know this equation where potential difference is W divided by Q, where V is potential difference. W can either be called work, energy, heat. Okay, either one of those. They all refer to the same thing. It's all about energy and things, what's happening. Q is charge, measured in coulombs. Also, you all know that, okay? You all know that. So, when we look at current is the rate of flow of charge. Okay, please, we don't say electrons, we say charge in particular. When we look at cells, when we look at batteries, what's happening inside those is quite complicated, which we are going to do at some stage. But there, it's not just electrons that are moving, but it is also positive and negative ions. So it's charge that's moving, not just electrons, okay? It's measured in amperes. Please, you may not say amps. That is not a recognized abbreviation, okay? It's an English abbreviation. We don't use it in science. You also know that I equals Q divided by delta T. All right, you've done this lots. I is current, Q is charge, T is time again. You may not use sec to do for time, because that's an English abbreviation, not a science one. Okay, this is very important. So, when we look at these questions, these are the ones on the electricity worksheet, which you should have with you in Teams, okay? And we're going to do some of them together, and then the rest you will do on your own, whichever ones we don't do, and you'll do the rest on your own. And from there, okay, the answers are on Teams as well. So, charge and current. Well, here's a nice easy question. A current of 7 amperes must flow through the kettle element for 3 minutes to bring water to the boil, and then they ask you to calculate the quantity of charge. They're asking for I. Guys, in this section, it's really important that you write down what you know, okay? Once you write down what you know, it's easier to know which equation to use. Therefore, current, 7 amperes. Time is 3 minutes, but remember, we can't work in minutes, we have to work in seconds. So we times by 60. Okay, so that's 180 seconds. Q equals I times T. I have just manipulated this equation. Okay, and we should probably rather have written it as I times delta T, which is 7 times 180, 1,260 coulombs. And it's huge. We get a lot of charge that goes through a system. Now, my problem here, please remember, 7 amperes is very, very big. 7 amperes can kill you. You need to be very, very careful. All right, let's just get rid of some of what I've got here, because you need to be able to read the question, though you do have it. All right. So, now they want the number of electrons passing through the element in one time. We are going back to what you know from electrostatics. N equals Q over QE. You know Q. You've just done it. You know the charge on an electron. You also 1,6 times 10 to the minus 19. Straightforward substitution. And we get a lot of electrons. Okay. Lots and lots and lots and lots and lots of electrons, which we expect. Okay. So, I want you to now do current and charge question 2 and 3. You guys can do that on your own. Okay, so that's what you're going to work on. Pause here, then carry on. We're now going to talk about resistance. Resistance is very important. Resistance is the opposition to the flow of charge. Resistors oppose charge moving, okay? It's measured in ohms. It's named after a scientist named George Simon Ohm. You can go look him up. It's a very interesting story, but I'm not going to tell you now. So now we get the equation R equals V over I. It comes from Ohm's law. You are going to use this equation over and over and over and over again. Resistance is ohms, V is potential difference, I is current. Now, we get R equals V over I from Ohm's law. To set up Ohm's law, to find Ohm's law, and do yourselves a favor, guys, go and play on the FET website or download the app onto your device and just work through it. They have lots of apps and lots of things you can do here which will help you understand this a little bit better, but it's always nice to work through it on your own. Okay, so what we have here is we have a rheostat. Okay, let's just go here. This is the important part. We have the circuit, so we can switch it on and off. Okay, we have our power supply, we have the ammeter to measure the current, and what we're going to keep is that's our resistor, that we're going to keep the same. Here we have the rheostat. Its function is to change the current in the circuit. Okay, so the rheostat changes the current in the circuit. Why? Because if I change the current, then you can change the potential difference. Okay, so the rheostat is a variable resistor. Its function to change the current. So in other words, current is my independent variable when I draw the graph. Potential difference is the dependent variable. When we get the graph, we get a nice straight line. It has to be a straight line. And it has to be a straight line through the origin. Because if there's no current, there can be no potential difference. Okay? Very, very important. So it's a straight line. V and I are directly proportional to each other. So in other words, okay, if I increase the current, potential difference has to increase. If I decrease the current, potential difference has to decrease. But only at a constant temperature. The gradient of the graph gives me the resistance. So if I have to work out the gradient, which is rise over run, it's change in potential difference over change in current. Very, 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 very important. Okay? So, that gets us to Ohm's law. The potential difference across a conductor is directly proportional to the current in the conductor at constant temperature. Please be careful here. You can't say circuit. We're looking at one specific part. Okay, we're looking at one part of the circuit, so we're looking at the conductor. Okay, or a resistor. You can also say a resistor here, that's fine. Alright, we normally say conductor because conductors really do have resistance. We don't often talk about it, but we assume that we have ideal circuits, which is why we don't consider it. Okay, so now that gets us to two different types of conductors. We get ohmic conductors and we get non-ohmic conductors. Ohmic conductors adhere to Ohm's law, so why they're called ohmic. So in other words, potential difference in current are directly proportional to each other, provided the temperature remains constant. Also, the ratio of V over I stays constant, and we get a straight line graph, which means the gradient gives me resistance. Nichrome wire, copper wire, aluminium wire, any of those wires, they are ohmic conductors. Non-ohmic conductors do not obey Ohm's law, and that's because of the way they are. That's because of their structure. Okay? We only work with ohmic conductors in all our calculations. Resistance changes. Resistance increases as temperature increases. the ratio of V over I can change, and what happens is we get a curve. Alright, now the gradient is the tangent to the graph, and you can see the gradient's constantly changing, which means resistance is constantly changing. And things like a light filament in the old filament light bulbs, in other words, tungsten, okay? Tungsten. Alright, that's really, really important. So, first part, number 4. A globe is marked 6 volts, 0.25 amperes. Calculate the resistance of the globe's filament. Well, they're telling me that's ideal conditions. So, V equals 6 volts. I equals 0.25 amps. R equals V over I. We put in what we know. It's 24 ohms. It's tiny. Well, no, it's not tiny. It's actually quite big. Alright. Then they ask you, why would the globe soon burn out? Burn out means it gets hot and it breaks if we use a 12 volt supply. Well, ideally, it should just be a 6 volt supply. Well, the current would then be too big, because if I double my potential, I have to double the current. That means it's going to get really hot, and then it's going to burn out. Okay, so the resistor will heat up too quickly, and the resistor will burn out. Okay, very, very important. The circuit of a starter motor in a car offers a resistance of 0.1 ohms to a 12 volt battery. Calculate the current drawn by the starter motor. Well, R equals 0.1 ohms. Potential difference is 12 volts. R equals V over I. So I'm looking for I, so it goes at the bottom. It's 120 because I is going to be 12 divided by 0.1. Okay, very important. Now they ask us something, and you're going to, when did we do this? The wire leading to the starter motor is short and thick. This has to do with resistance, and I'm hoping you remember this from grade 9. But it's to reduce the resistance, okay, so that we can have a large current. It's also why, once you learn to drive, you need to be careful, or if you ever have to jump start a car, you have to be very, very careful, because the current that goes through is incredibly large, okay, and this at 120 amps, it will kill you. Okay, so we're going to stop there, and we'll carry on next time.